Welcome to The Explainer. Today, we're diving right into the invisible muscle that powers our modern world, electric drive systems. Think about it. From massive industrial hoists to high-precision manufacturing robots, or even just a factory conveyor belt that magically adjusts its speed when heavy weights get dropped on it, you're watching an electric drive system in action. So we're going to break down exactly how these incredible systems actually work, focusing heavily on their five main components, how they handle different mechanical loads, and the brains behind the whole operation. Here's our roadmap for today. First up, the drive system anatomy. Then, converters and controllers. Third, the mechanical load. Fourth, we'll hit torque and speed characteristics. And finally, matching motor to load.
All right, let's jump right into section 1, the drive system anatomy.
Whenever you look at a standard electric drive architecture, it really boils down to a brilliant, continuous loop of energy and information. You've got your power source feeding into an electronic converter, which then drives the motor to actually do the physical work on the mechanical load. But here is the really cool part. There's this critical feedback loop. The controller acts like a master conductor, pulling in data from the load, the motor, and the converter, and then dynamically adjusting its commands on the fly to keep everything perfectly balanced. It's crazy to think about, but every single drive system out there, regardless of scale, relies on just these 5 fundamental components working in perfect sync. You have the power supply providing the juice, the electric motor turning that into motion, the power converter shaping the electrical flow, the controllers acting as the brains of the process, and finally the mechanical load, which is just the actual physical work getting done. That is the whole shebang. Moving right along to section 2, converters and controllers. Like I mentioned earlier, the controller is absolutely the brain of this entire system. Its whole job is to constantly match the motor and the power converter to meet the demands of the load, which in the real world are usually shifting all over the place. Imagine a heavy piece of material suddenly entering a milling machine. That's a massive, sudden load increase. The controller senses that instantly and adjusts the power flow so the machine doesn't just bog down, keeping that operational speed exactly where it needs to be. But the brain needs some muscle to carry out those orders, right? That's where power converters step in. They execute the controller's commands by literally modifying the raw electrical supply. Depending on whatever specific frequency or voltage the motor demands at any given millisecond, the system uses different types of converters. We're talking rectifiers, choppers, inverters, or cycloconverters. They essentially massage that electricity into the exact shape needed for the task at hand. Okay, let's look at section 3, the mechanical load. So to really figure out what a load is demanding from our system, we have to quantify its mechanical power. Mathematically, mechanical power demands, or P, are simply the product of operating torque, that's T, and the rotational speed, which we call omega. And just as a quick side note, omega is a function of the operating speed, N. But to put it all in plain English, the physical power you need is directly tied to how much twisting force is required, multiplied by how fast it needs to spin. It's really that straightforward. When you map out this relationship, it's fascinating to see how power scales against speed depending on the torque demand. For instance, if you have a constant torque load, the power required just goes up in a straight, linear line as speed increases. But if the torque is proportional to the square of the speed, well then the power requirement rockets up exponentially on a steep curve. It's a great reminder that different industrial tasks scale in completely different ways. Which brings us perfectly to section 4. Torque and speed characteristics. Now, the actual operating torque is determined by rated speeds using a very specific fundamental equation. And there's one little exponent in there, we call it the K value, that is an absolute game changer. That tiny number is the critical variable defining exactly how the rotational speed relates to the twisting force you're going to need. So by looking at that K value, we can actually group pretty much all physical demands into a few distinct behavioral profiles. If K is 0, the torque doesn't care about the speed at all. It's totally independent, like a hoist just pulling up a heavy static weight. If K is 1, it's linearly dependent. Bump K up to 2, and now torque is proportional to the square of the speed. You see this all the time with things like fans or propellers. And then, kind of wildly, if K is -1, torque is actually inversely proportional to speed, which is really typical for heavy milling machines. If you plot these different K values out, the profiles are so distinct. A K value of 0 just gives you a perfectly flat, constant torque line for those hoist operations we talked about. A K value of 2 forms this dramatic parabolic curve. Think about a fan spinning up. Air resistance squares with the speed, so you suddenly need exponentially more torque just to keep it accelerating. And that K value of -1, that actually slopes downward. This is because an application like milling needs massive, high initial torque at low speeds to literally cut into metal, but once it gets going for high-speed finishing, it actually requires way less torque. All right, let's wrap this up with Section 5, matching motor to load. Obviously, different types of electric motors, whether you're looking at synchronous, induction, or DC motors, have their own unique speed-torque curves. The real magic of system integration is taking those motor profiles and overlaying them directly onto the specific mechanical load curves we just examined. The ultimate goal here? You want to pick a motor that can supply the required demand without stalling out, while your controller constantly works to keep the entire operation hovering right at the exact precise intersection of those two curves. That's the sweet spot. So this all brings us to a final thought I want to leave you pondering. We've just seen how beautifully these 5 components balance out to match electric motor physics with intense mechanical demands. But as modern automation pushes for heavier, faster, and way more dynamic physical work, we are talking about everything from advanced robotics to massive renewable energy grids. How are these fundamental systems going to evolve? How in the world will the controllers and converters of tomorrow adapt to handle the totally unprecedented and unpredictable loads of the future? Something to think about. Anyway, thanks for hanging out with me for this explainer, and keep learning.